Very good evening to everybody. Can you all see the screen?
Yes, sir.
Yeah. So I welcome you all cordially to the 7th webinar of DiagnoPool, and it's our honor that we have today Dr. Sumati Madam. Dr. Sumati is the professor and HOD of East Point College of Medical Sciences, Bangalore, and she is a well-known NABL assessor. She is a technical assessor. And about our guest speaker, so Madam has previously held the position as the HOD of Biochemistry at Sri Devaraj Medical College, Kolar, and she has a rich experience in biochemistry as a technical assessor in conducting audits as per ISO 15189-2012. And needless to say, she is a very good academician and has several publications to her credit in national and international journals. More than that, I would say Madam is very humble and very approachable, and I was very happy that Madam accepted the offer to come to this very small forum to impart her vast knowledge in this field. And today's topic in particular is very challenging for me. I find very challenging, so I'm sure there was no other person better than Dr. Sumati ma'am to explain the concepts of bias, imprecision, and total allowable error. I will be stopping the screen now. Over to Madam. Yeah. Then you can present your screen now.
Am I audible now?
Yes, ma'am, you're audible now.
Thank you, Dr. Zubair, for the wonderful introduction. I must thank the DiagnoPool for accepting me as a guest speaker for a topic which is very important for all the laboratory physicians. And I wish, I will be able to do a justice in making them understand the total error in a very simple way. So, thank you very much. So, let us. I hope my slides are visible.
Not yet, ma'am.
Is it visible now?
No, ma'am. You have to present your screen, ma'am.
Yes, I am presenting. Is it visible now?
No, ma'am.
Okay, 1 second. No, my screen. Is it visible now?
Yeah, now you're presenting. Yes, ma'am.
Okay. Yeah. Okay. So thank you so much. So we shall have a great learning experience in understanding imprecision, what is bias, and what is total error in clinical biochemistry. So before we go into the topic as such, so I'll be giving you brief introduction, basic concepts of total error, bias and imprecision. Then we'll move on to what is actually total allowable error. And then we'll also discuss about what are the analytical goals what we have in the clinical chemistry for total allowable error. So now, as a healthcare worker, as a laboratory healthcare worker, so today all of us in clinical chemistry or in the laboratory as such, there are day to day we come across this scenario where we have to release the quality reports on a timely manner and which suit for the diagnostic purpose. So there is a lot of pressure in releasing a quality report at the right time. So we can go through this picture which is self-explanatory. So what we can see here is...
Slides are not moving, ma'am. Yeah.
Is it moving now?
No, it's not moving.
But I can see the...
Can you go for present? Yeah, F5 and you can present then.
Is it visible now?
Yeah, I think you should go for F5, man. The whole screen is.
F5. Control F5 or just F5?
Just F5.
Just F5. Yeah.
Where is it?
F5 again.
Yeah, the function button F5 you can press, it will come. Otherwise, now we can see. It's not a problem. This also
You can see, right?
Yeah,
Okay.
no issues. Yeah.
Okay. Thank you so much.
Yeah.
So this picture is a self-explanatory where we have a lot of variations we come across in the testing process. So a lot of interferences from the patient perspective and also the factors which influence the test result from the other perspective, that is the laboratory perspective and the environment around. So in the patient perspective, so we have some unavoidable variations, for example, age of the patient, gender, the medical treatment, what they are taking, history, any pathological conditions, the diet, stress condition, all these are the factors which influence the test result. And of course, these are not controllable, but if we take evidence of these things when we are taking the blood test, definitely it will help us in correlating the test result with the clinical condition. And other factors include the sample technique, the sample site, and of course where we are collecting the sample site, and the factors, other factors which influence the sample stability, that is the sample storage, the container what we use for the sample collection, and the patient identification. All these come under the errors which happens before the sample reaches to the laboratory. So these errors are called as pre-analytical errors. And of course, we know that when the sample reaches to the laboratory, there are number of errors which can be expected inside the laboratory itself. So the way we handle, the way it is transported to the laboratory, the way it is packed, the way it is stored during the transport, the temperature, stability, all those things. And in the laboratory also, we come across this type of errors which are called as analytical errors. So hope you have an idea about what are the types of analytical errors which can happen in the laboratory. So we have random errors and we have systematic errors. So we are going to discuss in detail about the random errors and the systematic errors. These are going to be the two important components in calculating our total error. And of course, after we analyze the report or before the report is being released, the errors which can happen at post-analytical part is the typographical error or any LIS interfacing error or any error which goes unnoticed can lead to this type of confusion. So the doctor is expecting something and what is delivered to him is something different. So all these errors are the total errors which can happen in a analytical process, that is in the laboratory, which includes the major component, the pre-analytical error, analytical error, and the post-analytical error. So you must be having an idea that out of all these errors, we have the pre-analytical error, which comprises of 65% of total error, and the analytical errors are 15%.
I'm sorry to interrupt. Again, it's not moving, ma'am. The next slide we are not.
Slide is not moving.
No, we are at the same slide of that variables. Yeah.
Is it now?
No, ma'am. It's not moving.
Now?
No, ma'am.
Okay. I don't know why it is not happening.
Are you able to see? Like we are seeing that boy with that stress sets, that the same figure. You know,
Okay. So is it now visible?
We have just
No.
yeah. Now we are seeing. Yeah.
Okay. So I'll go without the slideshow then.
Yeah.
I think slideshow is not working thing. So
No
I'll
issues.
go without the slideshow. Okay. So and we have the pre-analytical part, which comprises about 65% of the total errors, which is a major concern in the laboratory. And analytical errors consist of around 15% and post-analytical errors around 20%. So as a laboratory physician, all of us wonder like how the test should be, to what extent the test should be to say it as a good quality, and how the lab should define these quality goals, and how to validate this test to suit the existing analytical goal, and what is the best way to achieve these goals. So all of us have this question in our mind to answer to all those things. So now most of the labs in our country and elsewhere, so we have these two processes which are routinely done, that is internal quality control and external quality control. So we are all having these two things, that is internal quality control and external quality control, is sufficient to define our quality goals, or is it the only thing what we have to do to define our quality goals? So when we look at the internal quality control, we are assessing the internal quality control on a daily basis. So this is a daily activity and this is a monthly activity. EQE is a monthly activity. So most of you must be having an aware that the statistical analysis what we do out of internal quality control captures something. So we analyze the internal quality control and derive some of the matrices based on the IQC data. So that is importantly the mean what we get out of the IQC data, the standard deviation, and the percentage CVA. So basically the internal quality control is an activity which depicts the reproducibility of an assay. So which is the how the assay can be reproducible on a consistent basis. So this is in terms, we call it as a precision. Okay. So that we are going to discuss in detail. So this IQC is entirely concentrated on assessing the precision of an assay. Whereas the EQE is a activity which is done to know the bias, or in terms of the accuracy. So these two things, though they are entirely different, but they are capturing something very important for the laboratory. So this is precision. The IQC represents the precision and EQE represents the accuracy part. So now, so we saw that only IQC and EQE as a separate entity which cannot be taken to assess our total error. So it has to be comprehensive as a whole to assess our quality goal or analytical goal. So we have several methods or several models which have been established to assess our analytical goal or analytical quality. So one important model which is proposed in earlier days, which has been in practice for quite a long time, is total error, calculating the total error. Then we have sigma metrics. Then we have method decision charts. Then we have sigma statistical quality control selection graphs and charts of operating specification. So each model is dependent on a statistical model, which is the data derived from the IQC and the EQE. So each model is quite different from each other, and it is vast also. So today in this session, we are going to discuss on the total error and total allowable error. So this concept was developed by the Westgard and team in 1974, who introduced this concept in a laboratory. But then the laboratories were capturing and they were following the error model, these two error models, that is systematic error and the random error separately. So there was no concept that the total analytical error in a system which comprises of both accuracy and precision. So these two errors were separately monitored. So then the Westgard came up with a concept to have a total error which comprises of both accuracy part as well as the precision part. So we have seen the accuracy is nothing but it's a activity. It's a how close your value to your peer value or your true value. So this process or it is a indication of any bias which is there in the system, so which is captured in the form of bias. So the errors, what we can expect in this process is systematic errors. The systematic errors are captured in the analysis of the accuracy part, and the precision is going to be captured by our daily internal control activity. So that is in terms of our percentage CV or standard deviation. So basically the total error comprises of both the systematic error, which is a representation of our accuracy part, and the precision, that is represented by our random errors. Okay, so it is both systematic error as well as random errors. So total allowable error is how much we can allow this error. So what is the target limit for these errors without affecting our clinical decision value? So within the clinical defined interval, how much error can be allowed? So that is the total allowable error. So total analytical error is quite useful metric both to assess the laboratory assay quality as well as to your quality goals. So this diagram represents a Gaussian distribution. So what is Gaussian distribution? So when we analyze a set of quantitative data, so in the laboratory, all of us do internal quality control on a daily basis. So we generate a quantitative data on a daily basis. So when you measure any quantitative data on a continuous basis, you get this pattern of graph, which is called as Gaussian curve. So in this, it's a bell-shaped curve, and you can see here there is a line. This is a central tendency. That means majority of the values will fall within this curve, and there is a central point which is called as the mean. Okay, which is called as the mean, and the points which are in and around the mean is the away from the mean from going forward and backwards is the dispersion. Okay, so this dispersion is calculated statistically by a tool called as it is represented as standard deviation. So we have plus or minus 1 standard deviation, we have plus or minus 2 standard deviation, and plus or minus 3 standard deviation. So up to 3 standard deviation, we are going to cover 99% of the data points which are going to be measured in that particular session. So this is the normal distribution, what is observed in a quantitative measurement. So these are the two things. As I told you, the total error comprises of the precision part as well as the accuracy part. So let us understand in detail what is precision. So precision is the closeness with each other of the large number of observations in measurement process and the prescribed condition. So how close the values are with each other. So when you have a large set of data points and a prescribed condition. So what do you mean by prescribed condition? So prescribed condition is nothing but the same measurement procedure and in particular environmental condition. Okay, so this is quantitatively expressed as coefficient of variation. So the precision is determined by your percentage CV. The least is your percentage CV. That means you have a very good precision. And there is something called as repeatability and reproducibility. So let us understand what is repeatability. So repeatability is how your data points are in relation with each other. That is how close they are with the successive measurements of the same specimen when you do it under same measurement procedure, same technologist, same measuring system, that means the equipment, under same condition in the same location. So basically everything should be same. All set of the conditions what we have in terms of the equipment, the measuring is your repeatability. And what is called as reproducibility. So in the earlier thing we saw that everything is same. So here reproducibility is under different conditions, but what remains same is the measurement procedure. That means the methodology of the procedure should be same, but you can measure the repetitive measurements can happen at by the different analysts, by using different equipment, by using different location in different locations and different days and different environmental conditions. So this is about the accuracy part. So we have understood what is accuracy. That means the closeness of these data points when they are measured in a successive manner and when we have a large set of data points. And what determines your precision is your percentage CV. So least the percentage CV, that means you have a very good precision. Now coming to the accuracy part. So accuracy is nothing but how your value is closer to your true value. How close you are to your true value. So what is considered as true value? So in internal quality control...
the slide is stuck at repeatability again.
No, sir. It is in accuracy.
Accuracy? Okay, fine. I'm sorry. Yeah. Okay.
Okay. So hope the audio is clear.
Yes, ma'am.
Okay. So when we say true value, so what is the true value? So when we analyze the internal quality control, so most of our internal quality controls are assayed controls. So that means the manufacturer has done this analysis on a wide range of platforms. So they have measured it on a different platforms and they will give us the target mean. So you can take the target mean from the kit insert what is being given along with the internal quality control. So that can be your true value. Or you have something called as peer mean. So the people who are using some of the controls such as Biorad, so they have a system called as Unity software. So here the Unity software captures the internal quality control data from various locations and they derive their peer mean on a real-time basis. So this mean can also be taken as a peer mean. So this mean is more appropriate because you have the peer mean set for particular lot number, particular reagent lot number. So it should suit your system as well as for that particular lot number. So this can be qualitatively expressed as in terms of bias. So we saw the accuracy is measured in terms of precision is measured in terms of percentage CV, and the same way the accuracy is measured in terms of bias. So what is bias then? So bias is the difference between your observed value, that means your lab value, and the true value. So true value is either you can take target mean or peer mean. And for the calculation purpose, so when we calculate in terms of percentage, so that can be put it as observed value minus true value divided by true value into 100 is your percentage bias. So hope the accuracy part is clear. So two things you have to remember is the the how close you are to the true value, and it is measured in terms of bias, and it is calculated as an absolute value, that is the bias itself, which is difference between the observed value and the true value, and the percentage bias, which is given as observed value minus true value divided by true value into 100. So this is a very familiar diagram to all of you, just to make it and reinforce again. So this is the diagram, first one, which represents the all the data points are scattered across the chart, so which is not even precise or not accurate. That means the data points, but there is no accuracy. That means it is away from the true value. So this is precise, but it is not accurate. Whereas the third one represents it is accurate as well as precise, because there is a closeness between the values as well as it is closer to target mean. So ideally our assay should be, so this is another graph which shows your precision and accuracy part. So this is a Gaussian curve. So what we get during the measurement of large data set in the internal quality control. So this is your set laboratory mean. The middle part, central tendency, is your laboratory mean, which is away from your true value. That is the target value. And this is your bias. That is the difference between your lab mean and the reference or the target mean. Lesser the bias, more is your accuracy. Okay, so the dispersion what takes place around the mean is your precision, which is represented in terms of standard deviation and percentage CV. So lesser your percentage CV, more precise your analytical process. So ideally, our any testing process should have both accuracy as well as precision. So in order to achieve this accuracy and precision, we need to decrease the random errors as well as systematic errors, which are the part of analytical process. So we'll come back to, so we have understood now what is the precision and how it is captured, what is accuracy and how it is captured. So as I told you, the analytical errors comprises of both systematic error and the random errors. And in analytical process, these are the two tools or metrics which we have to capture systematic errors and random errors. So as I told you, accuracy is represented in terms of bias, which will capture the systematic errors, and the imprecision part, that is the precision part. The imprecision is nothing but the random errors which are captured in terms of percentage CV. And these are the two matrices which we are going to use for the calculation of total errors. So before going to the total error calculation, so let us understand what is random error. So what is random error? Random error, as the name suggests, it is very random. It is not consistent. You will not see the no deviations on a consistent basis. So some of the points may go suddenly out of the acceptable limit. So it varies on a day-to-day basis. So there you can see a large dispersion around the mean, around the true value. So these are observed in most of the LJ charts. So you will have to pick it up, and very difficult to find the root cause for the random errors than systematic errors. But you will still have to do the root cause analysis and see what is wrong with the system. And these are the most common causes for the random errors. So when you have improperly mixed or dissolved reagents, some air bubbles in the system, clots, microclots, unstable power supply, frequent temperature fluctuations, your pipetting errors, and poor operator techniques. So this graph shows your systematic errors. So systematic errors are very easy to identify because they are consistent. You will see this kind of deviation on a daily basis. So these systematic errors, these data points will be shifted on either side of the mean, so either above the mean or the below the mean. So there is a deviation from the central tendency. So this pattern you will see in the systematic errors. The most common causes for systematic errors are whenever there is a log change. You might have observed in the LJ chart. As soon as there is a log change, your curve will deviate. So you will have to observe there is some change in the lot and what has gone wrong with the lot. And the calibration expiry, when your onboard calibration is expired, you will see this trend. And improper calibration technique, reagent contamination or expired reagents. And if you have QC material prepared and kept for a long time and if it is not stored appropriately, there are chances of deterioration of QC material. And when there is a malalignment of your pipetting probe in the system, which can give rise to a systematic error. Wrong assigned calibrator values, and if there is a sudden change in the testing process. So let us not go in detail about how to do the root cause analysis and the corrective actions for random errors and systematic errors, because we'll have to move on to the total error and total allowable errors. So I just wanted to make you understand what are the possible causes for random errors and how to identify them, and what are the possible causes for systematic errors and how to identify them. So now coming back to the total error. So as I told you, so we have understood the precision and how to identify and the systematic error and the random errors. So now the total error comprises of bias and imprecision. So it is a total of your systematic error and random error. So it is mathematically it is calculated as bias plus 1.65 standard deviation. You can take 1.65 standard deviation, or you can calculate the percentage form of total error by calculating the percentage bias plus 1.65 percentage CV. So if you want to calculate percentage total error, then you need to use percentage bias and 1.65 into your CV, percentage CV. You as a laboratory physician will need to know the total error as such, because some of our guidelines, they give absolute numbers and also they give it in percentage. So I'll explain you that in the later part. So now we'll see this graph. So why have we taken 1.65 SD for calculating the total error? So here, so as I explained you earlier, I showed you a Gaussian curve. This is the data which is dispersed around the mean. This is a central tendency. So this is the dispersion. We have a limit of including 3 SD data points. So when you go from 1 SD, that is a green line what you are seeing here, when you take 1 SD, which includes 68% of your data points. Okay. And when you include 2 SD limit, it includes 95% of your data points. And when you include up to 3 SD, plus or minus 3 SD, we can include up to 99.7% of our quality control data. And rest is excluded from the analysis. And it is considered as outliers. Okay, so why this is important? Because we have to capture the errors also within the set of limits. So here we, for calculation of total error, we have included 1.65 standard deviation. So which comes somewhere in between 1 SD and 2 SD. And rest 5% from here and 5% from here is excluded. So that is why it has been excluded. You can see here, because your errors will also include bias. So when you have a bias, your Gaussian curve will move either towards the positive side or towards the negative side. So when you can see in this diagram, so there is a central tendency here. So this is your lab mean, which is moved away from your target value. That is your target mean. So this is the part which covers the bias. Okay. So this rest 5%. So we have included in the total error calculation up to 1.65 dispersion, only up to here this limit. Okay, rest 5% is excluded. But here, for total error calculation, we are also including the bias. So bias also includes this part of the dispersion. So which is again the 5% of your dispersion. So in order to avoid the over calculation of error, so this 1.65 ST is taken as a limit, not the 2 ST. Hope it is clear for you. Any doubts you have till this?
Ma'am, only this step can you explain again, ma'am?
Yeah. See, when we are calculating the total error, we are calculating the bias as well as the dispersion part, that is the random error. So when we are including the dispersion part, that is the random errors, we are calculating up to 1.65 ST alone, not the 2 ST, because ideally it has to be taken 95%, but when you take 1.65%, the 5% part of this is excluded. Why? Because this 5% of this part is included in the bias calculation. So for the bias, we are including the entire part, right? So this 5% is again, if you take that 2 ST, this 5% of it is again you are going to add it into your error system. So 5% of your addition error calculation, it will overshoot the required quality control set. So in order to overestimate the errors, we are going to take only the 1.65 ST, not the 2 ST.
Okay.
Is it clear? Because you just think only the 5% is excluded from the other side because it is included in the bias calculation, and it will prevent the overestimation of your error.
Okay.
Okay. So yeah. So now we'll come back to the application of total error. So now we know that total error is both your systematic error and the random error. So if the total allowable error, what is total allowable error? So it is the amount of an error that can be tolerated without invalidating the medical usefulness of the analytical result. So without compromising on the clinical decision values, how much error we can permit in your system. So if your total error, what you obtain in your laboratory, if it is lesser than your total allowable error, that means your patient results are considered reliable. If your total error in your analytical system exceeds the total allowable limit, that means you are failing to meet the quantity specifications of the test result, and it is likely to be producing clinically unreliable patient test results. So now we have an example of calculation. So I thought I'll share you the practical way of calculating it. I have just arbitrarily put the mean values and the true value of the HbA1c level 1 QC. So let us see how we can calculate the total error for this. So the mean for the QC level 1, the lab mean is 5.5 and the true value is 5.3, that is the target value, and the SD is 0.2. And how do we calculate the systematic error? So systematic error is basically the difference between the mean, your lab mean, and the true value. So that means 0.2. How do we calculate random error? It is 1.65 into SD. So 1.65 into SD is 0.33. So now what is your total error? Total error is systematic error plus random error, which is 0.2 plus 0.33, which is total of 0.53. So now this is an absolute number. That means my error limit for HbA1c is if I get a value of 7.1. So in the 7.1, my error limit, my quality specification is 7.1 is 0.53. That means I can stretch my this thing up to 7.1 plus or minus 0.53. So this is the absolute number. So our quality, some of the guidelines which is given by CLIA and NGSP, they define this TE in terms of percentage. So for that we need to calculate percentage total error. So that means percentage bias to be calculated plus 1.65 into percentage CV. So bias is nothing but observed value minus your target value divided by the true value into 100. So that gives 3.8 and 1.65 into percentage CV. Percentage CV is calculated by ST divided by mean into 100. So that will give about 7.43. So the total error of my system in terms of percentage is 7.43 for HbA1c. So according to the guidelines which is given by National Glycohemoglobin Standardization Program, the allowable error is 6%. So which is quite higher than the defined quality goal. So I'll have to look into what has happened with the internal quality control and our EQAS. So this is how we calculate the total error. Hope it is clear for you all.
Yes, ma'am.
Yes, ma'am.
Thank you. Now coming to the what are the different guidelines available to know about the total allowable error. So the group of the clinical experts framed a different set of the guidelines which is available right now in the country and the global this thing. This is called as Stockholm hierarchy. That means the hierarchy is from this. So the first preference should be from this point, that is the starting point, and it goes down like this. So our topmost applicable guidelines should start from the medical requirements. So medical requirements in the sense we have certain parameters which are critically important for the medical decisions. So for the treatment purpose. So some of the parameters, not most of the parameters, we have defined total analytical goals, that analytical goals for the parameters based on the clinical decisions. So that we are going to discuss. And the next one is, the next choice should be biological variance database. The third preference should be proficiency testing guidelines. And fourth one is using proficiency testing results. And fifth is Tom's rule, that is TEA can be calculated from using biological reference intervals and also derive the TEA from the percentage CV. But always remember, when you do not have the guidelines for the above mentioned quality control guidelines, you can use the last resort for the Tom's rule and the current lab CV. But otherwise, in any given point of time, you have to go from the first point itself, that is the hierarchy should be followed from the medical decision requirements according to the parameter. Okay, so as I explained you regarding some of the parameters where we have the specifications given by some of the guidelines. For example, for HbA1c we have NGSP guidelines which specifies plus or minus 6%. For lipid profiles, we have the guidelines specified by National Cholesterol Education Program. So accordingly, we have for total cholesterol plus or minus 9%, HDL 13%, LDL 12%, triglyceride 50%. So these are the guidelines which we have currently for these parameters. However, some of the parameters are in the pipeline. Whereas if you don't get these specifications in the clinical guidelines which is set by the organizations, we can move on to the next guidelines which is available, what is called as biological variation values. So here this diagram shows that there are variations which can happen in an individual itself and across the individual. Say for example, in an individual, the test results can be affected by the diet, the gender, the body mass, body weight, and the medications, disease conditions. So all these factors, host factors, they influence the testing process. The result of a test, it can correlate with the test results or it can act as a interference itself for the test result. So there are a lot of variations inside, within the individual and across the individual. So based on this, we have there is a data for the large set of data available based on the different biological variations which are considered within the individual and across the individual. So we have three different sets of biological variation database. So this first one is the optimum. So optimum will give a stringent quality control set values, and the desirable is appropriately good for the beginners, and the minimum specification is the most lenient. They have a broad range of analytical goals. So it is always advisable to take the desirable biological variations database. So this is the table how it looks, biological variation database. Here you can see the parameters, and the biological variation CVI is the intra-individual imprecision, and the CVG is the inter-individual imprecision. And the last three columns what we are seeing here is the desirable specifications, that is imprecision part, the bias, and your total error, allowable error. So this is what is given by the biological variance database. This is freely available to download from the westcard.com. So they have a large set of parameters included in this biological variance database. However, some of the parameters we do not have the BVD guidelines. And now we have the other guidelines which is most commonly followed in most of the laboratories is the CLIA guidelines. So the CLIA guidelines specifies the goal as the percentages. So we have seen 10 plus or minus 10%, plus or minus 15%, like that. So or it can give plus or minus absolute values. So we can see the plus or minus for calcium we have plus or minus 1 milligram per day. So it can be absolute value or it can be in terms of percentage. CLIA also gives the range of SDs. So plus or minus 1 SD, plus or minus 2 SD, or plus or minus 3 SD. So this is some of the assays which is depicted here of the CLIA guidelines. So you can see for amylase, aspartate aminotransferase, we have in the percentage. Whereas for creatinine, when you can see, it defines in terms of absolute numbers, target value plus or minus 0.3 milligram variation is allowed, and it also has a percentage, or whichever is greater you can take it up. And for creatinine kinase isoenzymes, it also gives in terms of ST, plus or minus 3 ST. So depending on that, you can adopt and calculate the total error. Yeah. So then we'll move on. So we have discussed about the medical decision values guidelines based on that BVD and the CLIA guidelines. So now we'll move on to how to establish your target TEA by using your proficiency testing results. When you do not have anything available in clinical decision, BVD or CLIA, you can go for this. So what you can do here is take the percentage CV of your PT testing. So PT report, sometimes they contain, most of the time they contain this percentage CV. So you take the average of minimum 5 or 6 months CV percentage and you multiply it by 3. So this gives you a error limit in terms of percentage. So suppose for example, if this is TA of the glucose, I have put it in. Month 1 has 88 mean and 3.5 ST and 3.9 CV. So likewise all 5 months, and I get the average CV and it is multiplied by 3, and 11.3 is your the acceptable total error. Okay, so whereas the CLIA gives 10% as the total allowable error. So if the CLIA or any other guidelines, if you do not have, so you can go for averaging the CVs of the previous PT report and multiplied by 3. The last option is your Tong's rule. If you do not have anything else, So this rule states that you can take 25% of your biological reference interval. Say for example, if I have biological reference interval for calcium 9 to 11 milligram per deciliter, you can take 25% of it. That is the upper reference range minus lower reference range divided by 4 will give you the 25%. So this will give you the absolute number. So my TA would be the target value plus or minus 5%, 5.5 milligram per deciliter. So this becomes your absolute value. So when you want to calculate in percentage of total error, so this difference, that is the upper reference range minus lower reference range divided by the midpoint of the reference range or the median value of the reference range. So here in case of 9 to 11 it is 10. So 0.5 divided by 10 into 100 will give you the percentage. So this is 5%. So CLIA has defined the acceptable total error for calcium is in the absolute value it is 1 milligram per deciliter plus a target value plus or minus 1 milligram per deciliter. So this can be used if you do not have any other reference. And always the last resort should be this. So we don't usually advise this. So still you can consider your current lab CV, or you can take average CV for some months and you can multiply by 3. So that will tell you about your allowable total error. And so this is about what we have discussed about the total error, how it is calculated, and what are the different guidelines available for total allowable error. Now, what are the applications of total error? So you can use the total allowable error for selecting an instrument. So when you look at the precision and the manufacturer claim in terms of percentage CV, usually most of the manufacturers, they give only the percentage CV. They don't give the bias. However, you can, when you are verifying when you are validating the equipment, you can go for the bias calculation and see how much the total error which can be obtained from a new instrument. So this can be applied while selecting the instrument. It can be applied for validating a new method, whether the new method is having a error limit of the same as the standard method, or you can compare with other reference method. And you can use the calculation of total error by evaluating the performance of an analyte ongoingly. This is what we do commonly. So when we do the internal quality control and external quality, ongoingly how we are improving. So that also can be done. And the comparison of results across the labs. When you want to compare your reliability and reproducibility and your quality goals with the other reference lab or peer group, so this TEA can be used as one of the tools. And it can also be used for the comparing of results across the instruments. So when you want to compare the results of the two instruments, you can take this as a tool and compare the TEA between the two equipments. So these are the different applications of the total error. So to summarize, so total error is nothing but it comprises of the accuracy part and as well as the precision part. Accuracy part is captured in terms of bias and precision part is captured in terms of CV. And total error is calculated by bias plus 1.65 ST. So I hope 1.65, why 1.65 instead of 2. So when you want to calculate percentage total error, you need to calculate percentage bias plus 1.65 into percentage CV. So your total analytical goals are defined by various guidelines, which is based on the medical decision levels, biological variations, PT programs, that is CLIA, and previous PT results can be used when you do not have any reference from the guidelines available, and you can apply Tonks rule by taking 25% of your reference value, and last result should be taking your average CV and multiplied by 3. So these are the different guidelines available for the total allowable error. So this completes my presentation. I hope I made it very simple. I don't know how much was this thing. So if you have any question, please, I'm happy to answer.
Ma'am, I have one question. When you told when we calculate the total error from the PT reports, you said we have to multiply by 3 the CV percent. Why should we multiply by 3?
Because it covers your larger, like here PT also has bias component. Yeah. So this covers your entire set of the errors which can be captured by the bias as well as by the imprecision. So it's basically 3 is to cover 95% of your data points, which will encompass your both systematic error and the standard systematic error and the random error. It is basically to include the 95% of your data points.
I think there's one question here. Shankari Madam has put that, Madam, if IQC is normal but EQAS is out of the range in a new equipment, what could be the possibility?
Yeah, so most of the times what happens when you have a suppose for example you have set a lab mean for the new equipment or existing equipment when you have started using the internal quality control and you have set the lab mean. But after some time, during this process, there are a lot of variations which can happen. For example, it can undergo multiple calibrations. It can undergo multiple log changes. It can undergo multiple environmental variations and so many things. So gradually, what happens? There are certain variations which goes on accumulating in the system, which may not be picked up by your system. So why? Because you would have set the broader SD. So you will have to look at your SD, whether the SD, what you have set is broad enough to mask your errors, or what is that, like whether you have set the right mean. So when you're always, my advice is when you're setting a lab mean, always please correlate with your peer mean ones, because your peer means will actually depict your actual mean, because they can be also, you can pick your peer mean based on your lot numbers. So when you correlate with your peer mean, you will come to know whether actually what you have established is nearing to your peer mean. So there should not be much bias in that. So gradually what happens when you set a broader ST, so all the data points, even if they have a systematic errors, it can be covered in the, it will be definitely covered in the broader ST. So you will not be able to pick up the errors. So first thing you will have to look at review the mean when you have some problem with the EQAS. So though the internal quality control is fine, but always review your mean against your peer mean, and you cross check your SD. If SD is broader, then re-evaluate your mean and set proper SD and observe for some time. Suppose still you are not able to find out this thing, do the root cause analysis completely by checking all the reagent part calibration, all other things. If there is no impact on the patient sample, still you can send few samples from your laboratory to the interlaboratory comparison and verify. But when you do interlaboratory comparison, see to it, it should be the same methodology as of what you are doing, and you can include 2 labs for the interlab comparison. So to make sure that you do not have any bias in your system. I think I answered the.
Yes, ma'am.
Hello.
Yeah, yes, ma'am.
Yeah. So any more questions?
Ma'am, for percentage CV reference range, in that article the table which you showed, should we take CVIG for percentage CV reference range?
Your voice was breaking, Dr. Sudhir.
Yeah, when we have to define the reference range for our coefficient of variation, which is the most preferred reference for that?
In the sense, what is a reference? What we take from the this thing, is it when we want to set our quality control based on the reference range?
Yes. So,
Okay, reference range.
Yes.
You mean to say reference range,
Yes,
what
yes.
we should take?
Yes.
Yeah. Ideally, the first choice should be your kit insert, but some of the parameters where it requires regulatory, we have some guidelines which are routinely monitored for medical decisions, like ADA guidelines and NCEP guidelines for lipid profiles. So when you have existing guidelines for the monitoring of the parameters based on the clinical decision, first choice should be that, and second choice should be your kit insert, and third should be from your either the textbook, because most of the kit insert they don't give the reference range as per the age limit and gender wise, and all those details may not be available. So if you have this thing textbook, you can take from the textbook or any other journals which they have established the reference range.
Any other questions here?
Madam,
Yes, please.
can we, you have suggested to multiply CV percentage with by 3, right? For this total allowable error.
Yeah.
Why we cannot multiply it with 4 if we want to add bias and imprecision both? Because imprecision itself is a 3 SD, like if we consider it as 3 into percentage CV plus bias 1 more.
Yeah. So it's a
Can
good
we?
question. Yeah, please go ahead.
Yeah, so that is what I wanted to ask.
Yeah. See, basically, please remember all of you, this is not a suggested, like this is not a routinely done way of doing the calculation of TEA. It should be your last choice. So don't go for it. First of all, my advice is not to go for it. So it is,
Okay.
So please, all of you, this is just the knowledge, this thing, information has been given, but this is not the practice which should be done by any of the laboratories. So that I am making it very clear. So always you go from so the hierarchy what I told, it is always from the medical decision levels you have to take, and then next the BVD, next the CLIA. So further, there are very few assays where there is no TEA guidelines available. So only in that case you go for the Tonks rule and the CV. So ideally CV into 3 is, it covers the 3 SD variation, which in that we can also cover the bias. So that is the concept, but exactly why the 3 CV is not into 3 is considered is the based on the statistical analysis, I believe. So exactly the reason behind including 3 even I don't know. Basically it is a statistical tool which will give you encompass the whole inaccuracy and the imprecision part. So this is what I believe. But please don't follow this thing in your laboratory. Into 3, CV into 3, please don't follow. Always take from the BVD or
standard guidelines.
Yeah.
Okay.
And you don't have that parameter in the list, then you can go for your PT, go for your Tom's rule or other things.
Okay. Thank you, ma'am.
Yeah.
I have a lot of people are requesting for some reference. So, which is the reference you will suggest for this particular topic?
Particular topic you can have, it is there in the Westgard website. These reading materials are available in the Westgard. We have in the TEACH textbook. We have in the TEACH textbook. Okay, you can go for this. And I also got this materials from the AACC, that is American Association of Clinical Chemistry.
Okay.
Yeah.
Divya, would you like to give the vote of thanks?
Yeah.
Thank you, ma'am. Thank you for such a brief and detailed presentation about the bias and errors. I thank each and everyone who have attended here. If there's no queries, we'll end the session. And I request all of you to fill the feedback form before you leave the session.
Sure.